20 trillion gallons of water slammed into one single American state in just over 2 weeks. And that number is so huge that almost nobody who hears it can actually picture what it means. Try to think about it for a second. 20 trillion gallons, that is not a typo, and it is not a made-up number for a movie. This really happened, and it happened in California. This is not a scary story about something that might happen someday in the future. This is the true story of a storm sequence so extreme that it turned California upside down in a matter of days. Rivers rose so fast that rescue teams could not keep up. Towns that felt safe for generations suddenly had water pouring through their streets. People lost their lives. Families had to leave their homes in the middle of the night with almost no warning. And scientists, the same scientists who study weather for a living, had to come up with brand new ways just to explain how much water was falling from the sky. Because the normal way of describing rain simply was not enough anymore. So how does 20 trillion gallons of water even fall on one state in just over 2 weeks? What does that kind of water actually do to towns, cities, and mountains? And why, even after all that water fell, was it still not enough to fix California's long-running water problems? Stick around, because we are going to answer every single one of those questions and walk through exactly what happened, step by step, so you can understand just how wild this event really was. Before we go further, if you find this as shocking as I did while researching it, please hit that like button and subscribe. Because stories like this take a lot of time and effort to dig into and get right, and it really helps this channel keep bringing you the truth behind the biggest weather events in American history. Now let us get into it. Let us start with the number itself, because your brain genuinely cannot process 20 trillion gallons without some kind of comparison to hold on to. 20 trillion gallons is enough water to cover the entire state of California and more than half a foot of standing water from one border to the other. Think about that for a moment. Picture every single city in California underwater. Picture every mountain, every desert, every farm field, every backyard, every parking lot, all of it, sitting under 6 inches of water at the exact same time. That is the kind of volume we are talking about here. And this was not some wild guess or an exaggerated number made up to grab attention. Meteorologists built real models using data from the National Weather Service, and they used real rainfall totals that were collected across the entire state during this stretch of storms. Scientists ended up giving this stretch a simple nickname. They called it an unrelenting parade of atmospheric rivers. That phrase alone tells you that this was not just one storm. It was storm after storm after storm, refusing to stop. Before we go any further into the story, we need to actually explain what an atmospheric river is, because, honestly, the name alone tells you almost everything you need to know. High above the Pacific Ocean, there are long, narrow bands of concentrated water vapor. These bands can stretch for hundreds of miles and sometimes even thousands of miles, just like a real river, except instead of flowing across the ground, they flow through the sky. According to NOAA, which is the National Oceanic and Atmospheric Administration, the most powerful of these atmospheric rivers can carry an amount of water vapor equal to 7.5 to 15 times the average flow of water at the mouth of the Mississippi River. Just stop and sit with that comparison for a second. The Mississippi River is one of the biggest rivers on the entire planet. It carries a massive amount of water every single day, and yet a single atmospheric river moving invisibly through the sky can carry more water than that. When one of these atmospheric rivers finally slams into a mountain range, like the Sierra Nevada in California, something dramatic happens. All of that moisture gets forced upward by the mountains. As it rises, it cools down very quickly. And once it cools, it comes crashing back down as rain or snow, often in absolutely staggering amounts within just a matter of hours. That is the basic science behind an atmospheric river. Now imagine that happening not once, but again and again and again. Here is where this particular event turned into something completely different from a normal winter storm. This was not just one atmospheric river passing through. It was 9 of them, arriving back to back over a span of roughly 3 weeks. Storm after storm barreled into California without giving the ground any real time to dry out. The rivers never got a real chance to go back down to normal levels before the next storm arrived. It was like getting hit by wave after wave after wave, with barely any time to catch your breath in between. During this stretch, a freshman student studying atmospheric science at UC Davis named Colin McCarthy became something of a public figure. He started calculating a running total of just how much water was falling across the state. He used a method that was originally borrowed from the Farmer's Almanac, and he combined it with rainfall estimates from the National Weather Prediction Center. His math was actually pretty simple once you break it down. He used the conversion that 1 inch of rainfall across 1 acre of land equals roughly 2,754 gallons of water. Using that simple formula and real rainfall data, he added everything up, and the result was jaw-dropping. In just 16 days since the storm sequence had begun, the state had already received an estimated 24.5 trillion gallons of water. And the storms were still not even finished yet. Now let us actually walk through what this looked like on the ground, because a number this massive only tells you half of the real story. San Diego opened the new year completely soaked. In just a single day, the city picked up more than 2 inches of rain, which put that day among the 15 rainiest days ever recorded in San Diego's entire history. Roads flooded almost immediately. Cars became stuck and stranded in rising water in the middle of streets. Drivers who were just trying to get to work or get home found themselves suddenly navigating roads that had turned into shallow rivers overnight, with no warning at all. As the storm track shifted, the heaviest impacts moved north and into central California. Forecasters were calling for 2 to 4 inches of rain along much of the coastline north of Los Angeles, with some especially vulnerable areas expected to see even higher totals than that. Up in the mountains, the story became even more extreme than what was happening near the coast. Along the lower, west-facing slopes of the northern Sierra Nevada, forecasters projected 4 to 8 inches of rain, with an absolute maximum possibility of reaching as high as 12 inches in the most extreme pockets. Higher up in elevation, all of that moisture turned into snow instead of rain, and it piled up in feet rather than inches. This created extremely dangerous travel conditions across the mountain passes that connect Northern California to the rest of the state, the same passes that thousands of people rely on every single day. The Russian River became one of the most visible symbols of just how much water this storm sequence unleashed onto California. After chain of these winter storms, the river swelled far beyond its normal banks. It surged through towns like Guerneville, sending floodwater directly into streets and neighborhoods where residents had felt safe for years, sometimes for their entire lives. Rescue teams worked around the clock in communities across Humboldt County, wading through rising floodwater to reach both people and pets who were trapped by the rapidly changing conditions. Imagine being asleep in your home, and within just a few hours, the water outside your door rises so fast that you suddenly need a rescue team to come get you out safely. That is exactly what was happening across parts of California during this stretch. And this was not just inconvenient weather that made people late for work or ruined a weekend. People died. As the 9th consecutive atmospheric river in the sequence finally began to fade, Governor Gavin Newsom confirmed that the storms had killed at least 20 people. At the same time, tens of thousands of people remained under evacuation orders across the state, many of them not knowing when it would be safe to return home. Levees breached in multiple locations. Roads washed out entirely in some areas, completely cutting off access for emergency vehicles and residents alike. Power lines came down under the combined weight of saturated ground, high winds, and falling trees, leaving communities sitting in the dark even as floodwater continued rising all around them. Try to imagine that combination for a moment. No power, rising water outside your home, and no clear way to leave safely. That is the reality that a lot of Californians were facing during this stretch of storms. Here is a detail that genuinely surprised a lot of people once the full scope of this event became clear. Right up until this exact storm sequence began, California had been suffering through a punishing multi-year drought. This was not a short dry spell. This was years of below normal rainfall that had been building up and building up. Reservoirs across the state, including massive ones like Lake Mead and Lake Powell, had been sitting at dangerously low levels for years leading up to this event. Water levels had dropped so low that they made national headlines on their own long before this storm sequence ever began. And yet, even after more than 20 trillion gallons of water fell across the state in barely more than 2 weeks, water officials pointed out something that shocked a lot of people. All of that water still was not enough to fully reverse years of accumulated drought conditions across the broader region. Let that sink in for a second. 20 trillion gallons of water, enough to cover the entire state of California in 6 inches of standing water, and it still was not enough to solve the drought completely. That single fact tells you almost everything you need to know about just how deep California's water deficit actually was. It took an event this historically extreme just to make a meaningful dent in the problem rather than solving it outright. The drought had been building for so long and had dug such a deep hole that even a disaster of this scale could only partially fill it back in. So why does an event like this happen at all? What actually causes 9 atmospheric rivers to line up and slam into the same state, one after another, with barely any time to recover in between? Meteorologists point to a specific and fairly common winter weather setup called a pineapple express. A pineapple express is a particular flavor of atmospheric river that draws its moisture directly from the warm tropical waters near Hawaii before slamming directly into the west coast of the United States. Because these systems pull their moisture from warm tropical waters, they tend to arrive warmer than a typical winter storm. And that warmth matters a lot, because it changes what falls from the sky. Instead of snow, precipitation from a pineapple express often falls as rain, even at elevations that would normally be receiving snow during a typical winter storm. Now here is where it gets even more dangerous. That warm, heavy rain often falls directly onto existing snowpack that is already sitting in the mountains from earlier storms. When warm rain hits cold snow, it speeds up melting. The combination, warm rain falling on top of existing snow, is exactly the kind of setup that produces the most dangerous flooding of all, because the melting snow adds even more water on top of what is already falling from the sky. It is like adding fuel to a fire, except the fire is floodwater, and the fuel is melting snow that nobody was expecting to melt so quickly. It is also worth understanding just how significant atmospheric rivers are to the West Coast, even outside of extreme events like this one. Under completely normal, non-extreme conditions, these systems are responsible for up to 50% of all the rain and snow that falls across the western United States in a typical year. Think about that for a second. Half of all the rain and snow across the entire western half of the country comes from these atmospheric rivers. They are, in a very real sense, the primary water delivery system for an entire region of the country. Without them, places like California, Oregon, and Washington would look completely different because so much of their fresh water supply depends on these systems showing up during the winter months. Research led by scientists at NASA's Jet Propulsion Laboratory has also found something else that is worth knowing. Atmospheric rivers are associated with roughly half of the most damaging windstorms recorded across the middle latitudes over the past 2 decades. That means the danger from these systems extends well beyond just rainfall totals alone. It is not only about how much water falls. It is also about the powerful winds that often come along with these storms. Winds strong enough to knock down power lines and topple trees, which is exactly what happened during this event in California. Let us take a moment to really think about the timeline of everything that happened here, because when you lay it all out end to end, it becomes even more clear just how relentless this storm sequence really was. It started with the very first atmospheric river making landfall and soaking the state right as the new year began. San Diego took the first major hit, with rain totals landing among the rainiest days the city had ever recorded. Then, instead of the weather calming down and giving the state time to recover, storm number 2 arrived, and then storm number 3. By the time meteorologists were tracking the 4th and 5th systems in the sequence, rivers across the state were already running high, soil was already saturated, and reservoirs that had been low for years were suddenly rising fast. Each new storm added more water on top of ground that simply could not absorb anymore. When soil is already completely soaked, new rain has nowhere to go except straight into rivers, streets, and low-lying neighborhoods. This is part of why the later storms in the sequence caused so much more damage than the earlier ones. Even in cases where the actual rainfall totals were similar, the ground itself had changed. It had gone from being able to soak up water like a sponge to being so saturated that it acted almost like pavement, sending nearly all of the new rainfall straight into rivers and streets instead. By the time the 6th, 7th, and 8th atmospheric rivers moved through, evacuation orders were already active in multiple counties. Emergency crews were stretched thin, responding to one flooded neighborhood while already bracing for the next storm on the radar. Mudslides became a serious concern in areas that had recently experienced wildfires because burned hillsides lose the vegetation that normally holds soil in place. Without that vegetation, heavy rain on a burn scar can trigger fast-moving mudslides with very little warning. This added an entirely new layer of danger on top of the flooding that was already happening across the state. Roads in these vulnerable areas were closed preventively in some cases, while in others, mudslides struck before crews could even get warning signs in place. When the 9th and final atmospheric river in the sequence finally arrived, exhaustion had set in across emergency response teams throughout California. Firefighters, rescue swimmers, National Guard members, and local volunteers had already been working around the clock for nearly 3 weeks straight. And yet this final storm still needed a full response, because even a smaller storm arriving on top of already saturated ground and already swollen rivers can cause serious new flooding. Let us go back to that number one more time, because it deserves a closer look. 20 trillion gallons is such an enormous figure that even scientists needed creative ways to help people understand it. One way to think about it is this. If you tried to fill up standard swimming pools with that much water, you would need more pools than most people could ever count in a lifetime. Another way to think about it is through the 6-inch comparison we already covered, imagining the entire state of California, from the northern border all the way down to the southern border, covered in half a foot of standing water all at once. But there is another comparison worth mentioning too. Remember that atmospheric rivers can carry an amount of water vapor equal to 7.5 to 15 times the average flow of the Mississippi River. Over the course of 9 separate atmospheric rivers hitting the same state, one after another, you start to understand how a number as massive as 20 trillion gallons becomes possible. It is not one dramatic event. It is 9 large events, stacked on top of each other, each one adding trillions of gallons to a total that just kept climbing higher and higher. Now, you might be wondering, why does this event still get brought up years later? Why does a stretch of storms from a single winter still matter so much to meteorologists, scientists, and journalists today? Part of the answer is that this event completely changed how experts talk about extreme rainfall. Before this storm sequence, most people, even many scientists, rarely use comparisons this dramatic to describe rainfall totals. But once the 20 trillion gallon figure started spreading, it gave everyone a new benchmark, a new way to measure just how extreme a storm sequence could actually become. Whenever a new atmospheric river event happens anywhere on the West Coast now, meteorologists often compare it back to this exact stretch, asking whether it could come close to that same 20 trillion gallon total. This event also changed how emergency planners think about back-to-back disasters. Before this happened, a lot of emergency planning assumed that communities would get some recovery time between major storms. This event proved that assumption wrong. 9 atmospheric rivers arriving in roughly 3 weeks meant that recovery time essentially disappeared. Emergency planners have had to rethink how they prepare for situations where one disaster rolls directly into the next, without any real break in between. There's also a bigger lesson buried inside this story about the relationship between drought and flooding, and it is a lesson that a lot of people find genuinely surprising. Most people tend to think of drought and flooding as two completely opposite problems. Drought means not enough water. Flooding means too much water. It seems like they should cancel each other out. But this event proved that reality is a lot more complicated than that. California went from a punishing multi-year drought straight into one of the most extreme flooding events in its modern history, and yet officials confirmed that the flooding still was not enough to fully solve the drought. How can that be true at the same time? Part of the answer comes down to how water actually gets stored and used across a state as large as California. A lot of the rain and snow that falls during a storm like this runs off quickly into rivers and out to the ocean, rather than soaking into the ground or filling up reservoirs in a way that can be used later. Reservoirs also have limits on how quickly they can safely capture floodwater, because letting them fill too fast can create serious dam safety concerns downstream. So even when trillions of gallons of water are falling from the sky, a significant portion of it does not end up stored anywhere useful for the long term. It rushes through rivers, causes flooding along the way, and eventually flows out into the ocean, without ever really solving the underlying drought problem that took years to build up in the first place. This event also highlights something important about how snowpack works in a state like California. A huge portion of California's water supply throughout the year does not come directly from rain. It comes from snow that piles up in the mountains during the winter and then slowly melts throughout the spring and summer months, feeding rivers and reservoirs gradually over time. This slow, steady melt is actually a really important part of how California manages its water supply across an entire year, not just during the rainy season. But when a Pineapple Express event brings warm rain instead of snow, or when warm rain falls directly onto existing snowpack and melts it too quickly, that slow and steady water supply gets disrupted. Instead of melting gradually over months, huge amounts of snow can melt suddenly, sending a rush of water downstream all at once instead of spreading it out gradually over an entire season. This is part of why officials were so concerned even while celebrating the fact that so much rain had fallen. Yes, the rain was desperately needed, but the way it arrived, in such a fast and extreme burst, created serious flooding risks and did not necessarily translate into the kind of long-term water security that California actually needed. Let us also talk a little more about the human side of this story, because it is easy to get lost in numbers like 20 trillion gallons and forget about the real people who lived through this event. Families across California had to make split-second decisions about whether to stay in their homes or evacuate, often with very little warning before floodwater arrived. Some people ignored evacuation warnings because they had lived in the same area for years without ever experiencing flooding that serious before. Unfortunately, some of those decisions turned out to be tragic, which is part of why the death toll climbed to at least 20 people during this stretch of storms. Rescue teams described genuinely harrowing situations, wading through fast-moving water to reach stranded families, sometimes in the middle of the night, sometimes in conditions where visibility was almost zero because of heavy rain and darkness combined. Pets were rescued alongside their owners in many cases, with rescue teams in Humboldt County specifically making an effort to bring animals to safety alongside the people who loved them. Shelters opened up across multiple counties to house people who had lost access to their homes, whether because of flooding, power outages, or roads that had washed out completely. For a lot of these families, this storm sequence did not just mean a few days of inconvenience. It meant weeks of disruption, damaged homes, lost belongings, and, in the most tragic cases, lost loved ones. It is also worth pointing out just how unusual it was for a college freshman to become one of the most quoted sources during a major natural disaster. Colin McCarthy was not a professional meteorologist with decades of experience. He was a freshman studying atmospheric science at UC Davis, using a fairly simple mathematical method to track the running total of rainfall across the state. But his numbers were accurate, his method was sound, and his willingness to share his running calculations publicly meant that regular people, not just scientists, could actually follow along and understand the scale of what was happening in something close to real time. His work is a good reminder that you do not always need decades of experience to make a meaningful contribution to how the public understands a major event. Sometimes it just takes someone willing to do the math, check it carefully, and share it clearly with people who are trying to understand something enormous and hard to picture. Now, let us circle back to the atmospheric rivers themselves for a moment, because there is more to understand about why they behave the way they do. These systems form over warm ocean water, where evaporation lifts huge amounts of moisture up into the atmosphere. Wind patterns then organize that moisture into narrow, concentrated bands, rather than spreading it out evenly across a wide area. This is actually part of why atmospheric rivers can be so intense in the specific areas they hit, while leaving nearby areas relatively untouched. The band of moisture is narrow, sometimes only a few hundred miles wide, even though it can stretch for thousands of miles in length. When that narrow band lines up directly with a mountain range like the Sierra Nevada, the results can be extreme, because the mountains force all of that concentrated moisture upward at once, wringing it out like a sponge being squeezed. If the same amount of moisture had been spread out over a much wider area instead of concentrated into a narrow band, the impacts likely would have been far less severe. This is part of why forecasters pay such close attention to the exact path an atmospheric river is expected to take, because even a shift of just 100 miles or so in either direction can mean the difference between a manageable rainstorm and a genuinely dangerous flooding event. Let us also talk about why the timing of these 9 storms mattered so much. If the same total amount of rain, all 20 plus trillion gallons of it, had fallen gradually over an entire winter season instead of in just over 2 weeks, the impact on California would have looked completely different. Reservoirs could have captured more of it safely. Soil would have had time to absorb water between storms instead of becoming completely saturated. Rivers would have had time to recede back to normal levels before facing new rainfall. But because 9 atmospheric rivers arrived back to back, with barely any real gap between them, the state never got that recovery window. Each new storm added its water on top of conditions that were already stressed from the storm before it. This is a really important lesson in how extreme weather works. It is not always just about the total amount of rain or snow that falls. It is also about the timing and the pace at which it arrives. The exact same total amount of water, spread out differently across time, can either be a manageable, even helpful, source of relief for a drought-stricken state, or it can become a genuine natural disaster capable of costing lives and causing billions of dollars in damage. As California moves forward from an event like this, water officials and emergency planners have had to seriously rethink how they prepare for the future. Some of the lessons learned during this stretch of storms have already led to changes in how certain reservoirs are managed, with some officials pushing for more flexible rules that allow reservoirs to capture more floodwater safely when extreme rain events happen, rather than being forced to release water early just to maintain safety margins. Other lessons have focused on emergency communication, making sure that evacuation warnings reach people faster and more clearly, especially in areas like Guerneville and other towns along the Russian River that have experienced serious flooding before and are likely to face similar risks again in the future. There has also been renewed attention on burn scar areas, the hillsides left vulnerable after wildfires, because this event proved just how dangerous those areas can become when heavy rain arrives on top of a landscape that has already lost the vegetation needed to hold soil in place. So, what should you actually take away from a story like this one? This event stands as a genuine reminder of just how much power sits within a weather pattern that most people outside the meteorology world had barely even heard of before this particular winter. 20 plus trillion gallons of water, arriving in barely more than 2 weeks, pushed rivers past their limits, forced tens of thousands of people from their homes, and tragically cost multiple people their lives. And all of that happened while barely making a dent in a multi-year drought that had been building for far longer than the storm sequence itself lasted. It is proof that a single type of weather system, one that most people cannot even see with the naked eye, since it exists as an invisible plume of moisture high above the ocean, can completely reshape an entire state's water situation and threaten lives, all within the span of just a few weeks. It shows how something invisible, something most of us will never actually see with our own eyes, can carry more water than one of the largest rivers on the planet, and can do it 9 separate times within a single winter. If this breakdown helped you understand exactly how something this extreme actually happened, please hit that like button because it genuinely helps. Stories like this reach more people who have never even heard of an atmospheric river before this video. If you are new here, make sure you are subscribed, because we are going to keep covering the most extreme weather events in recent history, along with whatever comes next, as California and the rest of the West Coast head into another winter storm season. Drop a comment and let me know if you were in California during this exact stretch of storms, or if you know someone who was. I read every single one of them, and I always find it fascinating to hear directly from people who actually lived through events like this, rather than just reading about them after the fact. Stay informed, stay curious, and I will see you in the next video.